Hello everyone. Now we are going to see about the design of asynchronous sequential circuit. Question was design an asynchronous sequential circuit that has two inputs x1 and one output z. When x1 equal to 0, output z is equal to 0. This is my first condition. Next, the first change in x2 that occurs when x1 is 1 will cause output z to be 1. This is second condition. Third is the output z will remain at 1 till x1 returns to 0. Now we are going to see the solution. Already we have seen the condition. When x1 equal to 0, z equal to 0. And your second condition is x1 equal to 1. At that time, x2 should change from 1 to 0 or 0 to 1. At that time, your z will be equivalent to 1. This is our second condition. We'll start from initial condition as 0, 0 and your output is 0. That means x2 and x1 equal to 0 and your output is 0. Already we know that your first condition is if x1 is 0, z is 0. So your first condition is we are assumed that 0, 0 it's your initial condition. If x1 is 0, your output is 0. So it can retain in the same state, and also we have two different state. So initial state 0, 0 means one bit alone can change to avoid the critical race condition. If both the bit are changing, critical race is occurring. So to avoid the critical race, from the initial state, any one bit has to change. So from 0, 0 to it can change to 0, 1 or 1, 0 state. So 0, 0 has been changed to 0, 1 or it can change to 1, 0. But we need to write the output. So if it is the same state means 0 in our output is 0. But if you see 0 and 1, 0 state, we have to write the output for this. So first we'll take the 0, 1 state. So already you know that if x1 is 0, your output is 0. But if you see this, your x2 is 0 and your x1 is 1. So your first condition is fails. And see the next condition, x1 equal to 1, your x1 equal to 1, but your x2 has to change from 0 to 1 or 1 to 0. At that time, your output will be equivalent to 1. Just see here, your x1 is 1, but your x2 is not changing from 0 to 1 or 1 to 0. It was in the same value or the same bit. So there is no change of bit. So if there is no change of bit, whatever the output is there for the present state, the same output should be there for the output. Next, if you see the 1, 0 condition, here we all know that if x1 is 0, your output is going to be 0. So this is the 0, 1 output and 1, 0 output. So already 0, 0 is over. Now we got a two new state. Take the 0, 1 state. So this is your 0, 1 state. Again, it can retain in the same state or else it can change to 0, 0 and 1, 1 state. So 0, 1 means your output is 0 in the same state. Then if you see the next state 0, 0, what is the output? We know the condition. Your first condition is if x1 is 0, your output is 0. Move to the next state, 1, 1 state. This is x2 and this is x1. Your x1 is 1. Your x1 is 1. Your x2, whenever your x1 is 1, the x2 has to change from 0 to 1 or 1 to 0. Then your output is 1. So now you have x1 equal to 1. Just check the value for the x2. Here is 0. The x2 is changing from 0 to 1. So whenever your x1 is 1, the x2 has to change from 0 to 1 or 1 to 0 and your output is 1. And your output is 1. And this condition over. Now move on to this condition, 1, 0 condition. 1 0 and your output is 0. It can retain the same state. Similarly, 1 0 can change to 0 0 or again 1 1 state. So it is in the same state and your output is 0. If you see this, x2 and x1 both are 0. Already we know that the first condition is if x1 is 0, your output is 0. If you see this 1 1 and you have to write the output. If you see the previous one, for this condition, if x1 is 1 but x2 is changing from 0 to 1, so your output is 1. If you see this condition, your x1 is 1, but if you see the x2, x2 is not changing. If there is a change in the x2, then your output will be 1. Here x2 is not changing, only your x1 is 1. So this condition is fails. So your output is going to be same output. Output is not changing. Next, if you see this, we have completed this condition. It's a new state. We have completed this state. It's a new state. If you see this, this is another new state as 1 1. Your output is 1. So you have taken another new state 1 1 and your output is 1. It can retain in the same state. Then it can change to 0 or 1 0. So your next state is 1 1, your output is 1. It can retain in the same state. This 1 1 can change to 0 1 and 1 0 state. Again, if x1 is 1, we want to see the x2. So your x2 is changing from 1 to 0. See this condition. Whenever your x1 is 1, the x2 has to change from or 1 to 0 and your output is 1. So here your x1 is 1, your x2 is changing from 1 to 0, your output is 1. And your next one is 1 0. Whenever your x1 is 0, your output is 0. So this condition is over. And see this one. This is another new condition or the new state. So 1 1 0. 1 1 and your output is 0. It can retain in the same state. This 1 1 can change to 0 1 or 1 0. Again, we have to write the output. If x1 is 1, we want to check your x2. x2 is changing from 1 to 0. So whenever your x1 is 1, x2 has to change from 1 to 0 or 0 to 1. Your output is 1. Next, 1 0. Already we know that x1 is 0, your output is 0. Again, we got another new state as 0 1 and output is 1. Take 0 1 and output is 1. It can retain the same state. 0 1 can change to 0 0 or 1 1. x1 is 0, output is 0. x1 is 1, the output is changing from 0 to 1, then your output is 1. So we want to repeat this process until the new state is not occurred. So here all the state has been repeated, so we can stop till here. So initially this state I have taken or else I have assigned as A, and this I have assigned as B, this I have assigned as C, this I have assigned as D, this I have assigned as E. But if you see this and this is also 1 1, this is also 1 1. But if you see the output, this is 1. If your state is 1 1, if your output is 0, that has been assigned as D. If your state is 1 1 and your output is 0, that has been assigned as E. And finally 0 1. Already 0 1 is here, but your output is 0, that has been assigned as B state. If your output is 1, that has been assigned as a F state. So like this, we have to derive this. Why we are deriving this? By deriving this, we want to draw the state diagram. Next, we are going to see the state diagram. If you see this, A state is initial state. it can retain in the same state, it can move to the B state, and it can move to the C state. B and C are the next state for the A state. So if you see this diagram, A is your present state, it can retain in the same state, it can move to B state, and it can move to C state. This is our first state assignment. Next, if you see the B, it can retain in the same state, it can move to A state, and it has been introduced a new state as 1 1, output is 1. So this we have as D. So now the B state, it can retain in the same state, it is moving to A state, and it is introduced a new state as D, and output is 1. Similarly, see the C. C is moving to A and E, and it also retain in the same state. C retain in the same state, moving to E state, and moving to A state. So like this, based on this, we need to draw the state diagram. So to draw the state diagram, we have done this one. Next, I'm going to show you how to write the primitive flow table. So this is called it as primitive flow table. So from the state diagram, you can write the primitive flow table. As usual, we all know how to write the state table. It's similar to the state table. If you see this, this is going to be the present state. If you see this, this is going to be the next state and output. So first write all the present state which we have drawn in the state diagram. How many states are there? A, B, C, D, E, and F. So totally we have 6 states. Write all the 6 states here. Next, for the next state and output, just write the values 0, 0, 0, 1, 1, 1, 1. So write 0, 0, 0, 1, 1, 1, and 1, 0 state. So as usual, so you know the state diagram. It can written in the same state. So if you are see the present state, already we have written all the variable or the state variables. If A is there, it is retaining in the same state, then that will be called it as the stable state. And for the stable state alone, we have to write the output in the primitive flow table. So if you see this, it is retaining in the same state, right? So 0, 0 means it is retaining in the same state. We have to write the output. Next, from A to it is moving to B as well as it is moving to Z. When it is moving to B, whenever 0, 1 at that time it is moving to B state. Whenever 1, 0 at that time it is moving to C state. So if it is A means it can retain in the same state whenever you have 0, 0 value. Your input is 0, 0 means it is retaining in the same state. If your input is 0, 1, it is moving to B state. Only we have to write the output for the stable state alone. What is stable state? Whatever the variable you have taken, it is retaining in the same state. That will be called as the stable state. So if it is A means it is retaining in the A state. If your input is 0, 0. So this is called as the stable state. So we have to write the output for this one. Again, we have taken A variable, it is moving to B as well as it is moving to C. So this is not a stable state. So we have to write it as a dash. So dash, it's mean that don't care condition. So it is moving to B comma dash and 1, 0. A is moving to B as well as C. So 1, 0 means C comma dash. And what about this one? We all know that both the bits should not change. So 0, 0 can't change to 1, 1. So we are writing this as dash comma dash. Next, if you see the B, again B means it is moving to A state. Whenever your input is 0 0, from B it is moving to A state. It can retain in the same state. Whenever your input is 0 1, B is retaining in the same state. So if it is retaining in the same state, that state will be called as stable state and your output is 0. The next is 0 1 can change to either 0 0 or 1 1. So this is as considered as from B to it is moving to D. Moving to D and your output is dash. Next 1 0. Your 0 1 can't change to 1 1 state. So this has been represented as dash dash. Similarly for C. C is retaining in the same state and you have written the output. And it is moving to A state and it is moving to E state. So we have written A and E state. So 0, 1 0 can't change to 0 1. We are writing dash comma dash. Similarly for D. D is retaining in the same state when your input is 1 1. When your input is 1 1, D is retaining in the same state. We have written the output. Where it is moving? It is moving to F state. When it is moving to F state, if it is 0 1, it is moving to F state. When it is 0 1, moving to F state. When it is 1 0, it is moving to C state. C comma dash. E. If you see E, 1 1 means it is retaining in the same state but the output is 0. It is moving to 1 0. 1 0 means moving to C state. 1 0 means moving to C state. And 0 1 means it is moving to F state. F comma dash. 1 1 to 0 0. It can't change. So this has been represented as dash comma dash. Finally, your F state. If it is 0 1, F comma 1. It is moving to A state whenever your input is 0 0. It is moving to A comma dash. Next, where it is moving? It is moving to D. D comma dash. This 0 1 can't change to 1 0 due to the critical trace. So we have written your primitive flow table. After primitive flow table, we need to draw the merge graph. Merge graph is nothing but if you reduce the primitive flow table, we can draw the merge graph. If you see A and B, compare the variable. Your output as well as the state should be the same as we have done in the state reduction. Already you know that how to reduce the state. Your present state as well as the output should be the same as well as your next state. If you see the A and B, here also A, here also A. 0. If it is dash means it's represented as don't care condition. So you can consider this as 0. So both are same. If you see this, this is B, this is B. This is dash, this is 0. This can be considered as a 0. Right? So this is also same. Both are don't care means this can be considered as a D and this is don't care condition, no issue. If you see the next one, C, here is don't care condition. So here we can consider this as a C and both are don't care condition. So your A and B are same. And if you see C, D and E, F, just check it out. What are the terms, what are the states was same. C and E was same. If you see C and D means here the variable has been changed. So you can't say that C and D are same. So you can combine C and E. Here is A, here is don't care condition and here is don't care and don't care. This is F, this is don't care and don't care, E and E, dash and 0. Right? Similarly C comma C and 0 and dash. And you can combine D and F. Here is A, don't care. Don't care means you can consider this as A. Here also don't care. Here also don't care. Here is F. Here is F. 1. Here you can consider as a don't care condition. Here is D. Here is also D. 1. Don't care. C. Don't care. And don't care. So you have combined A and B, C and E, D and F. already we have seen the state reduction in the primitive flow table. So we have combined A and B. A and C also can be combined. So what are the variable can be combined with the other variable? So A can combine with B as well as A can be combined with the C. Similarly, C is combined only with the E, and similarly D is combined only with the F. So this is the merge graph. So after reduction we have to draw like this. A comma B, that should be considered as a S naught. For the simplification we are writing like this. C comma E, this has to be taken as S1. Similarly, D comma F should be considered as a S2. So after the primitive flow table, we have to draw the merge graph. How we are going to draw the merge graph? By reducing the primitive flow table. This is the assumption we have considered, right? Next, we are going to see the reduced flow table. If you see the reduced flow table, just we have taken the primitive flow table. Already here we have the A, B, C, we have reduced, right? So whatever we have reduced, that has been written here. We have to write, this is the reduced primitive flow table. Already we have seen the primitive flow table. We have drawn the merge graph by reducing this. So we have seen the A comma B is going to be the same. So we have to write all the stable state. If it is 0 0 means it is going to be stable state. If it is B means 0 1 is going to be the stable state and output is 0. And D means we know that if it is 1 means we have to write D comma dash. 1 0 means C comma dash. For S1, C comma E is going to be the same. So 0 0 means A comma dash, 0 1 means F comma dash, 1 1 means E comma 0 and C comma 0. S2 means D comma F. A comma dash, F comma 1, D comma 1 and C comma dash. This is the reduced primitive flow table. We have reduced from the primitive flow table. Already we have seen the reduced flow table, but there we have written A comma B and C comma E and D comma F. Here I have removed that and we have taken the assumed value. A comma B means I have taken as 0 0 and that has been considered as S0. Similarly, C comma E means S1, S2 means D comma F. So we have assumed the value for all the three states 0 0 0 and 1 0. Now you know that, see this and write this table. If this is A, you can write S0 and output is 0. If it is B, as considered as S0. If it is D means it is considered as S2. So we are writing S2. If it is C, we have to consider as S1. So we are writing S1. So see this variable and see the assumed state assignment, and based on this replace this value in terms of S0, S1 and S2. After replacing A, B, C, D, E and F in terms of S0, S1, S2, we got the reduced flow table. If you see the reduced flow table, first one you have S0, S0, S2 and S1. There we don't have any issue. If you see the 0, 1, it is changing to 1 0. S0 means 0 1 is changing to 0 0 or else 1 1, but it can't change to 1 0 state, right? So here your present state is 0 1, but if you see the next state, it is moving to 1 0 state. So what we have to do to avoid this critical race, we are introducing one more state as S3 state. Just see the below flow table. Here in the left side you have the present state as 0 1 state, and if you see the next state you have the 1 0 state. So 0 1 state cannot change to 1 0 state. For that, we are introducing one state as S3 state, right? Similarly, if you see the last condition, S2 is 1 0. It can't change to 0 1 state, right? So here also we are introducing S3 state. First one, we don't have any issues. 0 0, again 0 0. Just I'm replacing the S0, S1, S2 and S3 value. S0 means I'm replacing 0 0. And if it is S2, it is 1 0. And if you see the S1, it is 0 1 condition. 0 0 is changing to 1 0 and 0 1 state. It is not changing to 1 1 condition. First row, we don't have any issues, right? If you see the second row, S1 is changing to S0, no issues, because 0 1 is changing to 0 0. But if you see the S1 is changing to S2, right? S2 means 1 0, S1 means 1 0. So it can't change from 0 1 to 1 0. For that, already we have introduced one state as 1 1. That is nothing but S3. So here, instead of writing S2, we have to write it as 1 1 state. 1 1 is nothing but S3 state. So how it is moving from 0 1, it is moving to 1 1, then it will change to 1 0 state, right? It is changing to 1 0 state. So in this way we have to do this. If you see the next one, 0 1 means it is retaining the same state, no issue. Again 0 1, no issue. And come to this one, because this state we have introduced to avoid the critical race. Now we'll come to this state 1 0, and S0, 1 0 is changing to 0 0, right? 0 0. Next 1 0 is changing to S2. Again it is retaining in the same state, no issue, same state, no issue. But if you see this, the S2 is 1 0 is changing to 0 1. We can't do that, because if you are doing this, critical race is arising. So to avoid this critical race, what we are doing, we are changing to 1 1 dash. So here also one state, here also one state, right? So next, what we said, we have introduced a state as 1 1. From where to where we have been changed? From 0 1 to 1 0 through via 1 1 state. So what state here has to come, that has to be written here. Here actually we have to write 1 0, but we can't write this 1 0. So we are writing 1 1 and then it is moving to 1 0 state. Similarly here, from 1 0 it cannot move directly to 0 1. So what we have to do, for S2, last condition has been assumed as 1 1. It is moving to 0 1 condition. So only we are changing this and this. So remaining we are not changing. So this 2 has been assumed as a don't care condition. Like this, we have to write the flow table, reduced flow table. Already we have seen this table, right? In terms of reduced flow table, we have seen this. Now we are giving a name for this as a transition table, right? For the transition table, this and this has been assumed as F1 and F2 as present state. This is your next state and your input. 0 0 0 1 1 0 and 1 1. This is S0, S1, S3, sorry, S2 and S3. So we have written like this. Next, take the flow table and write it here. Now by using this, we are going to do the K-map. If you see this, F2, F1, F2, F1, and this is X2 and X1. Your output is Z. Here we are going to find the answer for the next state, F2 plus and F1 plus. How we are going to do means, this is your present state, F2 and F1, right? So we have written in the F2 and F1. We have taken the input X2 and X1. We have written here. So if you see this, this is 0 0, and see the next state 0 0, right? This is 0 0 0 and 0. It's mean that how many variables, how many states was there? 1 2 3 and 4. Here also you have 1 2 3 and 4 states. So totally you have a 16 boxes, right? So first one is 0 0 0 0 0 0 means we have to write it separately for x2 and x1. This is for f2 plus and this is for your f1 plus. We are going to find the answer for your f2 plus and f1 plus. If you want to find the answer for the f2 plus, we have to consider the x2 values. If you want to find the f1 plus, we want to consider the x1 values. Then finally you're going to find the answer your z. If you take this, this is 0 0 and in the next state 0 0. What is answer? This is 0. Here we have written 0. Next is 0. Next is 1. 0 0 0 0 0 0 0 1 0 0 1 1. This means, what is the meaning of this? 0 1 3 2 4 5 7 6. So similarly we have to take the value and substitute and find the answer for f2 plus f1 plus and z. After finding the answer for f2 plus f1 plus and z, draw the logical diagram. This is nothing but asynchronous sequential circuit. So this is the way to design the asynchronous sequential circuit. Thank you.